Hey everybody, chapter 6 is on optics of the eye, and so the first part of this chapter is all about electromagnetic waves. Fortunately, we've seen already waves a couple of chapters ago, and a lot of what we did in that chapter will carry over. Um, because an electromagnetic wave is, first of all, just a wave, just that has a lot of the same properties that we've talked about. So light consists of these electromagnetic waves. When I write EM, that's what that means. Electromagnetic waves, where the electric and magnetic fields oscillate back and forth. So there's an electric field, and there's a magnetic field. The strength of that electric field, which we called E before for electric field, is going to oscillate. It's going to get big and small and big and small and on and on. And then there's also going to be a magnetic field, which will get big and small, and it will oscillate in a way that is opposite the electric field. And actually, I draw it in 2 dimensions here, but it actually exists in 3 dimensions, where the electric field is in one plane and the magnetic field is in another plane. So it's like they're 90 degrees to one another. Anyway, you just need to know that the light consists of these oscillating electric and magnetic fields. And at their very core, EM waves are caused by moving electrons. I'll put a link to this animation on Wikipedia, but in short, a radio antenna, I know we don't really see radio antennas that often, but you have one possibly on your car, is a metal rod, and on that metal rod you'll have electrons that will move back and forth, back and forth. They oscillate along that metal rod, and when they oscillate, they generate these oscillating electric and magnetic fields, which is light, and it conveys information in a particular way. So at their very core, electromagnetic waves are caused by moving electrons. That's true for visible light too, by the way, that when I have an atom with my nucleus surrounded by orbitals, electron orbitals, if I have an electron here and it jumps down to a lower energy level, then it will emit a light wave, a visible light wave, or a different energy light wave. So electromagnetic waves are always caused by moving electrons. Moving electrons generate EM waves. Electromagnetic waves have all the same wave properties as other waves. A couple of chapters ago, when we learned about waves, they had several different properties that we dealt with. That was the speed, or V. They also had a wavelength. Remember the wavelength, if I look at a snapshot graph, the wavelength is the distance from peak to peak, or trough to trough, from one point on the wave to that next identical point on that wave. And then also the frequency. The frequency, remember if I'm looking at a history graph, and have 2 different waves, one like this on the top and one like this on the bottom. This one has a higher frequency, and this one has a smaller frequency, or a lower frequency. All EM waves travel at the same speed in a vacuum. And that is C, the speed, is equal to 3 times 10 to the 8th meters per second. You don't need to know that speed, but you need to know that electromagnetic waves, or light, will all travel at this same speed, which is equal to 300 million meters every second. So it travels pretty fast. That's one thing, too, that's different about light from other waves, that light can travel in a vacuum without a medium, and this is something that really puzzled scientists for a long time. But you can have these oscillating electric and magnetic fields in a vacuum, that you don't need a medium for those. That you can still have these EM waves even though you don't have a medium, and that's not true for other mechanical waves. The electromagnetic spectrum has a range of frequencies. And I want you to know the EM spectrum. I want you to know the major parts of it: the gamma rays, the X-rays, the ultraviolet, the visible, that's what we see, the infrared, microwaves, and radio. You need to know all of these, and you need to know how they vary by energy, frequency, and wavelength. So these gamma rays are high energy, and radio waves are low energy. I might ask you to arrange these in order of descending or ascending energy, increasing or decreasing energy. I also want you to know about the frequency. These have higher frequency, look, I've written right there, and these have lower frequency. Frequency is always proportional to the energy. So a big frequency means a big energy. And then for wavelength, you need to know too that these have a really short wavelength. See, like the wavelength there is really, really short, and down here the wavelength is a lot longer. Radio waves can have wavelengths that are many kilometers or hundreds of kilometers or even thousands of kilometers long. They can have very large wavelengths. That's why shortwave radio is used, because they have really long wavelengths, even though it's called shortwave. They have really long wavelengths, and you can bounce those long wavelength signals off of the atmosphere and make them go all around the world. The energy of an electromagnetic wave is given by the frequency. I said that earlier. E is equal to a constant times the frequency. So really all that I want you to know here is that the energy, actually I wrote E, but let me write energy, so that we're not confusing it with the electric field, but the energy is proportional to the frequency. And here H is a constant, Planck's constant, where that has a value of 6.63 times 10 to the minus 34. And let's see, what's that going to be? Hertz per joule. No, I'm sorry, joule per hertz, or joule seconds. Okay, I have a couple videos I want to show you. Oh, I do want to just remind you, let's do a little reminiscing for a moment. Do you remember when Planck's constant has risen in this class? It came up when we were talking about standards for measurement, that the Planck's constant is the underlying standard of measurement for the unit of mass that we use for the kilogram, not just in the metric system, but since the British system is based on the metric system, which it is, then we use it for all standards of measurement for the unit of mass. It is the Watt balance, but it is based fundamentally on the Planck constant. Okay, let's try the next part.